All right, so let's continue on and finish up section 9.3. So we have a theorem, and it's going to get us basically our limit convergence test, limit comparison test. Theorem 9, let a sub n be a sequence of positive terms. Suppose that a sub n is equal to f of n, where f is a continuous positive decreasing function of x for all x greater than or equal to some n. Then the sequence from n equals n to infinity of a sub n and the integral both converge or both diverge. And so that's what we're going to look at. This is called the limit comparison test. Basically what we want to do is we want to build a function that is exactly like our sequence at all the values of n. And yeah, that's how this is going to work. So let's ask this question. Does this sum from n equal 1 to infinity of 1 over 2 to the n converge or diverge? And actually I need to slide my camera over because I don't think you're going to be able to see all of it. Otherwise, let's make sure we can see it all. Sorry, you're staring at my face for just a second. Yes, okay, you can see it. Great. So we want to know if this sequence of 1 over 2 to the natural log of n converges or diverges. So the really obvious function to work with is f of x is 1 over 2 to the natural log of x. This is certainly all positive, right? We need this to be a continuous function, we need it to be positive, and we need it to be decreasing. It's certainly all positive. Natural log is going to be positive when x is greater than 1, so that's not a problem. It is decreasing. Natural log is an increasing function, which means 2 to that power is increasing, and 1 over something that's getting bigger is going to be something that keeps shrinking. And it is continuous. Natural log is continuous on its domain, and, well, 1 is certainly inside of that. So we have exactly what we want. So let's evaluate then this integral of this function and see if we get that it converges or diverges. So we have the integral from 1 to infinity of 1 over 2 to the natural log of x dx. And you can see I continued on, but before I do, we have to make some substitutions. So I'm going to let u equal the natural log of x. And if u is natural log of x, that implies that x is e to the u. And that's important because du is 1 over x dx, which still has an x in it, and we don't have an x up there. So I multiplied both sides by x, and then I made that substitution for x and called it e to the u. So I have u is natural log, and e to the u du is equal to dx. Oh, and then finally, if x is 1, if you plug in 1, u is the natural log of 1, and you just get 0. So that changes our integral then to the integral from 0 to infinity of e to the u over 2 to the u du. So then I pulled the exponent out to give me a fraction here, e over 2 to the u. And in order to do this integral, which is infinite, we are going to evaluate the limit as b goes to infinity from 0 to b of e over 2 to the u du. And that works out very nicely because we have an antiderivative for any base to a power, and it's just 1 over the natural log of that base times the base to the power. So we're evaluating the limit as b goes to infinity of 1 over the natural log of our base times, and now here you can see I plugged in b and 0. And anything to the 0 is 1. So this is going to diverge because as b goes to infinity, since this base is bigger than 1, it's also going to go to infinity. So this whole thing goes to infinity. The limit or this integral diverges, and so by the integral comparison test, so does our original sum. So there you go. That is section 9.3. Thank you.